I'll list them briefly here. So we have annual conference where the research talks take place, and many junior women participants get opportunity to present their work in a form of short contributory work talks or posters. And we also have a 1.5 day mini workshop. So that is held often in non-metro cities. This idea is to reach out the people from different part of India. And we have mathematical workshop for young women, which is meant for undergraduate women in mathematics. So this is a very intense session in mathematical training, and it runs for 10 days. In fact, we are planning to have twice in a year this one. And then we have visitor program where around 3 established women, they go around in non-metro cities and deliver lectures and interact with women mathematicians. So idea is to here to popularize mathematics by presenting our mathematics students role models. So all these activities are generously supported by NBHM, that is National Board for Higher Mathematics, and CWM, that is International Mathematical Union Committee of Women in Mathematics, also provides financial support. In fact, so far for many courses they have given the support, and in past they have given financial support to invite women from SAARC country and vice versa. And so one of the other activities we have started since last year is a 3 series of online mini courses. So this year's first such series is starting today now, and we are honored to have Professor Rajeeva Karandikar as a speaker for this one. So hope you enjoy the talk and participate actively. Thank you very much.
Now I request Abhay to introduce Professor Rajeeva Karandikar.
It is my great pleasure to introduce Professor Rajeeva Karandikar. Professor Karandikar obtained his PhD at the ISI Kolkata in 1981. He spent some years as a visiting professor in USA and returned to ISI Delhi in 84 as an associate professor. He became a full professor in 89 and served as head of the Department of Maths and Stat at the institute, and also as head of the Delhi Center of the institute. He has been a visiting professor at several universities in USA and Europe. For a few years, he was an executive vice president analytics in Crane Software International Limited. He returned to academics in 2010 and became distinguished professor at the Chennai Mathematical Institute, where he was the director from 2011 till 2021. Currently, he is Professor Emeritus at Chennai Mathematical Institute. Professor Karandikar has made significant contributions to various areas, including stochastic calculus, filtering theory, Markov processes and Martingale problems, limit theorems, Monte Carlo techniques, queuing theory, game theory, theory of option pricing, etc. He has authored 2 books, one on filtering theory and one on option pricing with Professor Kalinpur. He is a fellow of Indian National Science Academy and Indian Academy of Sciences and has been awarded the Young Scientist Medal by Indian National Science Academy. He is a recipient of prestigious Bhatnagar Prize, C.R. Rao National Award in Statistics, and P.C. Mahalanobis Memorial Medal awarded by Indian National Science Congress. In December 2022, Professor Karandikar has been appointed as a chairperson of the National Statistical Commission. Professor Karandikar has been an editor of Sankhya and on the editorial boards of Annals of Probability and Journal of Statistical Planning and Inference. Professor Karandikar has been involved in numerous consultancy projects over the years. He has worked on development of proprietary block cipher algorithms for Indian Defense Services. Professor Karandikar has been involved with opinion polls and exit polls in India since 1998. He has worked with India Today, Doordarshan, TV Today during 1998 to 2005. From 2005, he has been associated with CNN IBN for opinion polls and has been responsible for all poll projections made on CNN IBN since the launch of the channel. Thank you. I will hand over to Archana.
Yeah, with just one thing I want to add. for participant, you are expected to maintain dignity and decorum at all the times. So please do not post which is not related to lecture. And in case you have a question, please post it in a chat box or in question. We will take up all questions at end of the lecture. And without further ado, I hand over the proceeding to Professor Rajeeva Karandikar. And thank you very much for agreeing for lecturing. Looking forward for your lectures. You can start now.
Thanks for this. Thanks for this invitation and introductions. And I'm glad to do this, especially because it is only online mode, so it was very easy to accept. Otherwise, it would have been one has to monitor whether you can travel this time and all that. But since it is online, I agreed right away, and it was not so easy to choose what topic to speak on, because my main research work has been in probability theory. Of course, consulting work hundreds of times, but this here I didn't want to speak about any consulting part. And then, the audience is primarily mathematicians. Some would be, of course, with interest and probability. Some may have even more interest and understanding teaching of probability, but large group may have very little. And the probability theory is very interesting, that even those who do research in probability theory, over the years I have met several, of course, and by half an hour conversation with them, I can make out whether their foray into probability has been just as a mathematician who treats probability as just an application of maths, or as a statistician or engineer who thinks about probability as coming out of some applied work. Of course, eventually they can do very, very important theoretical work, but what was the beginning? So there are both aspects to probability. One is the math part, one is the actual applications part. And what I plan to do is, of course, the focus will be on the math part, but within the math part, of course, let's say the proportion of mathematicians who are very comfortable with measure theory is very small. And whereas all lectures on probability theory at this level for Martingales and beyond begin with measure theory, and that cuts off again a large group of people who are potential users of probability theory. So I have chosen to do introduce Martingales, but on discrete probability spaces. The advantage is that we can most of the time, or almost all the time, we can forget about anything to do with integration theory and Lebesgue theory and this and that, and just look at it as a simple thing about counting or algebra, and what meaningful things one can do with that. So that is my plan. And so it will, since it's 4 lectures and we don't have a fixed agenda, it is going to be very slow. We'll go over the things. All right, so let me. Yeah. So martingales and stop times are powerful tools which are very useful in studying various aspects of probability theory in applications. In particular, these notions are very useful in, say, mathematical finance. So martingales are defined by a notion called conditional expectation, a powerful idea in itself, but for full generality it needs measure theoretic framework, which puts off lots of people. In these lectures, we will be considering, therefore, random variables taking countably many values, and then one can define conditional expectations, martingales, stop times without bringing in measure theory, making it accessible to a wider group. So it will all be defined as functions on finite or countably finite, countably infinite sets, and so one can, depends on one's liking, one can treat every proof as coming as a algebra, or one can treat the proof coming as a thing about counting, and so on, or simple part of analysis. All right. Now, so for those who are only interested in mathematical techniques, the first part is addressed to them. The probabilistic ideas and techniques also given alternate proofs alternate approach for proofs of results which may have nothing to do with probability theory. So this can be thought of as just a tool. For example, the Weierstrass approximation theorem. It's a more or less first course in analysis, or at best the second course in analysis, definitely real analysis, definitely one comes across the Weierstrass approximation theorem. And this is one such example. I will talk about the probabilistic proof of Weierstrass approximation a little later today. But before that, I would like to draw everybody's attention to this Wikipedia page on what is called probabilistic method. This is due to the origin goes to Paul Erdős and about it's for combinatorics, and Paul Erdős used this for proving existence of a prescribed kind of mathematical object. So wants to show that there exists a point with certain properties, and it works by showing that if one randomly chooses objects from a specified class following a specified probability system, then the probability of achieving what you have is strictly positive, therefore it is non-zero, therefore there is a point. So this was the idea initiated, I mean at least written by Erdős. Maybe it was there in vogue or earlier also. And this has been applied in various other areas of mathematics such as number theory, linear algebra, real analysis, computer science, information theory. So once again, the original problem one is interested in have nothing to do with probability. There is nothing random about it. There is no probabilistic thing in the statement or the conclusion in the theorem. And yet, by bringing in probabilities externally and getting out through those tools, one can get a mathematical proof. Okay. Now, one question sometimes asked to me by students is that on one hand we are taught that gambling is bad by school, by parents, that you should never do gambling. That is, at least all achha bachchas are taught that gambling is bad. While in mathematical curriculum they have a course called probability, and most examples are about coin toss or dice, questions which only gamblers must be interested in. So the students have asked me that why should we study this? On one hand no gambling, on the other hand you teach us this coin toss and so on. Well, first of all, it cannot be denied that probability theory has its origins or major chunk of its origins in gambling. Okay. That cannot be denied. There is more to it, but that's beyond. So, you would have come across the name Cardano in various contexts. And this is a Wikipedia page on him. He's a mathematician, physicist, physician, biologist, physicist, chemist, astrologer, ... and the last one says gambler. And the Wikipedia page I am reading that he was notoriously short of money and kept himself solvent by being an accomplished gambler and chess player. And he made money using gambling, which he used to do maths. He wrote a book. I can't read, I won't attempt to read the original title, but in English it is Book of Games of Chance, written around 1564 but published only 1663. This is the first systematic treatment of probability. So from here we can conclude that there is some link with gambling in development of probability theory. It cannot be denied. But the Wikipedia also says that he used the game of throwing dice to understand the basic concepts of probability. So more about this particular sentence in a few minutes. So there is another thing called problem of points, again a Wikipedia page. Without going over it much, I'll just say that the Wikipedia says that it was proposed and to Blaise Pascal, and Pascal had a correspondence with Fermat, and through their discussion they provided a convincing self-consistent solution to the problem, and then also develop concepts that are that are still fundamental to probability theory. So Cardano, Pascal, Fermat, they contributed to the development of the mathematical aspects of probability theory. De Moivre, whom we all learn as school kids, De Moivre Laplace, De Moivre's complex numbers construction and De Moivre's theorem, etc. The description on him is also that he, because of various religious issues, he had to move out of France and went to England. While he was a friend of Isaac Newton and others, they encouraged him. He became a fellow of the Royal Society but did not get a job. That was the way the world was. And he lived on a modest means which he generated by his sessions advising gamblers in a coffee house. Okay. So, again, a mathematician who made a living by advising gamblers. So, he is the other person who has written a book on probability theory called Doctrine of Chances. And it said that it had been prized by gamblers then and continue to be. So, however, so these are the gambling aspects, but probability theory along with statistics has applications to various walks of life. Physics, medicine, economics and finance, communications, cryptography, and the list keeps growing every decade. Recent times, of course, COVID, we all suffered through COVID, and we can imagine how the world would have been if the COVID vaccine was not available. And the development of not just COVID vaccine, but any vaccine and most medicines that we are used to is based on a combination of statistics and probability and using it to figure out how humans respond to this particular medicine or vaccine. Remember, there is no vaccine which will cure everybody, just like there is no medicine which will cure everybody of a given ailment. It has to be based on what proportion, and that there comes statistics and probability. Now, online banking usage. Well, most of us, even some of us may have been using online banking even before COVID and lockdown, but everybody was essentially forced to do online banking because of the COVID. You can't go out, you have to buy things, you have to do this, you have to do that. And so we are sharing information with our bank and giving instructions, and that requires cryptography. And that requires, again, understanding of probability and statistics. What some may wonder that, okay, cryptography needed mathematics, you understand, but where is probability coming in? Okay. So remember, even if a user is non-believer in probability and he says he'll use crypto, but after all, it's algebraic object and there is no problem with crypto. But to decide which algorithms are good and which are not so good, if you don't resort to probability theory, you may not, but somebody who wants to attack and get hold of money from your bank account, you can't prevent that person from using tools in probability. So therefore, one has to be aware of what tools in probability can be used to attack encryption being used, and unless one does that, one will end up in a disaster. So probability theory does play a very important role in crypto and online, everything that we do online. Now, most of you would have heard of something called digital signature. Signature, we all know. You get a form, there is a dot somewhere, you have to write your name and sign on that, and that is taken as you have done it. You can you have to sign a check and give instructions. That is understandable. Giving instruction to the bank using internet and so on, okay, it is understandable. You have used encryption, etc., etc. But this digital signature refers to you create a document and then you sign it digitally. And it can be then shared on internet, or it can be then printed along with everything else. And this is treated on par with the standard signature. In India, the IT Act of 2000 enabled digital signatures. And it's a interesting, again, in a way it doesn't use probability, but what algorithms to be used as digital signature, you have to again resort to probability theory. So the purpose of this was that probability theory is everywhere. Now, most examples in books and also in this lecture are going to deal with tossing of typo. Tossing of coin has become tossing of coins, but tossing of coin and tossing of dice, which appear to be related to gambling. So why this dichotomy? If we talk about such wide areas where it has applications, then why give examples in gambling or related to gambling? The reason is that it is possible to precisely state the conditions behind the experiment one is trying to model, so that we can focus on the core issues related to probability. If we start talking about the approval of vaccine for COVID, it will start with so many questions that would be very difficult to agree and resolve, that we get bogged down by that. The same applies to various other applications. So to understand what are we trying to do, it is best to start with examples where you can completely describe all our given conditions. So therefore there is nothing left undescribed, and then it can be treated mathematically. Okay. So one has to understand this as we are just trying to understand what is doable and then apply it to a given context. That is why examples are coming from coin toss or something which appears to be akin to be gambling. But its implications are a lot more. Okay. So in the first part maybe even 90%. I really don't know how far we will go and where we will stop. But therefore, for most of these lectures, we will consider a framework where omega, as is popular in probability literature, it's a countable set. And for every omega in capital Omega, called an elementary event, we have a function from the elementary event set to unit interval, 0 and 1 included, and it is such that the summation of all this is 1. So the points omega are thought of as some experiment is happening, one omega will appear, which little omega, we don't know which little omega is going to show up. We have listed all which may show up, and assigned with each is a number which we call probability of that particular outcome, and it has to be assigned in such a way that the summation is 1. And then subsets of omega are called events, and we define the probability of the event as P of A summation over P of omega, or omega in A. So we can think about a toss of a dice. Dice has 6 faces, 1 to 6. So omega we can treat it as 1, 2, 3, 4, 5, 6. That's a finite set. Every omega in that is just 1 or 2 or 3 or 4 or 5 or 6. We can think about it as the outcome which will occur once we toss the coin, once we toss the dice. And this talk is before the tossing of the dice. Okay. Now we have to assign numbers so that they add up to 1. Now, depending on what you know of the dice, if let's say the dice is such that one face, it is 2 parts. One part is let's say metal, and the other part is plastic, and they have been glued together. So the metal part is heavier, and therefore if we toss it, the metal part is likely to go down and the plastic part is likely to show up. So therefore, to begin with, we can say that, well, we don't know exactly what will occur, but the chances, heuristics notion of chances is that the number of dots on the face which is entirely metal is going to be very low. The one which is entirely plastic is going to be high, and then the other 4 will be kind of, let's say, equal, because you don't know which of these 4 places it may come. So in general, there is no God-given rule which will say that if you toss a dice, all probabilities have to be 1/6. So if you toss a fair dice or a symmetric dice or uniformly constructed dice, no differences anywhere, then it stands to reason to believe that all these are equally likely, and then we treat this as our starting point. So initially, when these things developed, the notions of what is a definition, what is a proof, all these are also evolving. So they defined what is equally likely and what is a probability, and what is equally likely if they have the same probability. So later it was attacked, saying that there's a circular definition. 2 events are equally likely if the probability of their occurrence is same, and what is probability, etc., etc. So now the best way to think about is that you have a set omega, you have assigned numbers on that set omega, you call each of them as a probability, and then we go on defining. Now, in a given context, it is up to us whether this assignment of probability corresponds to our understanding of the phenomena or the event or not. Okay. So we have thereby separated this. So now it is strictly a mathematical object. Even if there is a non-believer in probability, everything here we are doing is kosher because it's only a mathematical notion. You can think about probability as a mathematical definition here and proceed. But to apply it to any of the context we talked about, we have to understand that the assignment of probability is something which is corresponds to our understanding of what is happening, and then the conclusions will also follow. Okay. So that is how one should look at probability. So the non-believers can continue to make sense of what the rest of the lectures by just treating probability as simply a function defined on our countable set, and everything it follows that way. Okay. And though not needed here, when omega is not countable, then we can resort to the measure theory. If it is it can be any arbitrary set, then we should define the probabilities in a suitable way such that something happens. I will not even list down what that is, but the starting point, we have a difference here. We have to be a lot more careful than this casual way of defining. Okay? Like if omega is a unit interval, you can't define length of every single point has to be defined 0. There is no other consistent way of defining, and the length of a interval cannot be defined as sum of lengths of points in there. That is the beginning of measure theory change, and the same thing one has to go through when we go to applying probability in those contexts, but we stay away from that most of the time. Okay, so we have defined omega, we have defined what are events. All subsets are events. Probability of an event is simply summation of p of omega in the set A. That is our probability of a set A. So point function, we have now treating it as a function on the power set. Now, if a random variable on omega is a function x from omega to r. So later, or not in our lectures, but one can treat random variables which take d-dimensional vectors, infinite dimensional vectors, and the works. But we are going to restrict ourselves to where talking about real valued random variables. Okay. So omega is a function, x is a function from our set omega to r, and its expected value. So I'm going to continue to use the terminology in probability theory, but our definitions are all very straightforward, defined as just something algebra on finite sets or countable sets. Okay. So expected value of x is defined as if omega is finite, or if our function is non-negative, then we simply define it has a weighted average. For a point omega, x omega is our value. You give the weight is p of omega and take the sum. So it is the weighted sum of the function, the weights coming from the probabilities, and therefore, if it's a finite sum, no problem. If x is non-negative, again no problem. We can always define. Otherwise, there is a problem. If we have infinite, omega is a countably infinite set, and x omega takes both positive and negative values, the definition on the right hand side and one here is ill-posed. You have to fix an order, and then maybe it is convergent, maybe it is non-convergent, and it could depend on the order of summation and all that. So more generally, when x is allowed to be not forced with non-negative and omega is countably infinite, Ex is defined if expected value of mod x is finite. Mod x is a non-negative function, so expected mod x is always defined. If expected mod x is finite, we also define expected x by the same formula. And this is exactly what we do if we do are into Lebesgue integration. So, but one doesn't have to understand what is Lebesgue integral to understand what we are doing. After all, first when we do sums of series and operations with series and so on, we have to go through the same sequence of work or same sequence of arguments. Okay, so we say that x is integrable if expected value of mod x is finite. If you are thinking of it as a function, if omega was natural numbers, and if you think about x, which is a function from natural numbers to r as a sequence, then the sequence is summable. If it is just not forced to be non-negative, then we'll say it is summable if this happens. But here we'll use the probability terminology, integrable. Okay, we can see that it can be seen that if you define the set S to be all those points in our omegas, all those points x in real line, such that probability that x equal to little x is positive, then we can verify that E of x is simply summation over x, p capital X equal to x. So let me go back. Expectation x is this summation. Now this x omega can take any of the, let's say it is only finite value. So we can look at all omegas, let's say it takes only 3 values, 1, 2, 3. So we can take all omegas where x omega is 1, all omegas where x omega is 2, and all omegas where x omega is 3, and write it as a double sum, and then we are summing over all omegas where sum over p omega where x omega is 1, but that's exactly probability x equal to 1. So by a very simple argument here, one can check that E of x is simply summation over x probability x equal to x. Okay. This is a since we are only dealing with integer valued, I mean we are in real valued, but our defining objects are only countably many, at most countably many. All these are very straightforward, verifiable assertions. Now, take phi to be a function from R to R, such that expected value of mod of phi x is finite. Now, phi of x therefore is a function from omega to r, so we can treat phi of x as also a random variable. And the given condition says that phi of x, y equal to phi of x is an integrable random variable. And then the second equation is again very easy to verify. It corresponds to proving the change of variable for Lebesgue integral, but here done in a much simple way. In Lebesgue thing also, we'll first do it for simple functions and then move on. So this is like using change of variable for simple functions in Lebesgue theory. Okay, so these are things which are very, very easy to verify. Now, so I'm calling property of E dot, that means property of this operation of expectation that we have introduced. So, so the class of objects on our for which expectation is defined is set of functions which are integrable. So it's not exactly a linear space. No, it's a linear space. Sorry, the linear space of all functions which are such that expected mod x is finite. All functions x such that expected mod x is finite, and there it's a linear space, and its properties can be just verified and checked. We have already talked about them, but I have written it here. That linear space linearity can be checked, and expected mod mod of expected is less than equal to expected mod, and this we can check from here very easily, because when we take mod of expectations, we are taking summation over x where x is positive, summation over x where x is negative. Wherever x is negative, we add it, call it only x. So then x, if x is positive, for when we take mod, we are just adding two things here. So we can verify that this equation, all these are very, very easy to verify, and therefore I have not written down. Those of you who are teaching, you can use these as exercises if you are teaching analysis, you can use this as exercise in your analysis course, even to BSc 1. Or college teachers, even the first time you teach analysis or calculus, when you bring in functions, you can use these as exercises. All right. The other thing is, once you prove linearity, u less than equal to v will tell you that eu less than equal to ev. So all we need is when v is positive, expected v is positive, and then apply 2 for that, and follow straightforward from definitions. And interesting thing is this number 6, that it's called Jensen's inequality for integrals, but for summation of sequences and so on, one can very easy to verify the Jensen's inequality when you have a convex function. Phi of summation, finite sum or countable sum, is less than equal to summation of phi of those values. That's all this thing says. Now, very important that this equation 5 and in the sequel, a statement like u less than equal to v means that omega, if you look at probability of the set of omegas where u of omega is less than equal to v of omega, it is equal to 1. In other words, if you go back to our definition of probability, we didn't rule out probability being 0 of a certain event. Okay. And so the u less than equal to v, we are saying that it should hold on all omegas for which p of omega is positive. If p of omega is 0, we really don't care what happens to u, what happens to v in our work. It is never going to happen, or in expectations it will not show up at all, because the weight of a 0 doesn't going to get added. Therefore, this will still be true. This is a technicality. We may as well start only with omega such that probability of every point is positive and don't have to add this. But there are reasons why we need that for generalities of various statements. Now, if A is the indicator function of a set, clearly expectation of indicator A is P of A. Because indicator takes two values 0 and 1, we have to take weighted average P of A, the weight is 1, P of A complement weight is 0, so the weighted average is PA, straightforward. Now, from here we get that for any integrable random variable x, one has this indicator is of course less than equal to 1 by theta mod x, because left hand side is 1 when mod x is bigger than equal to theta, and the right hand side then is greater than equal to 1. So this is a trivial inequality, but this along with the fact that we had proven as u less than equal to v implies eu less than equal to ev, it follows that probability mod x bigger than equal to theta is less than equal to 1 by theta expectation mod x. So something which is so trivial to prove for countable omega, and those who do integration, we can see that the same thing one can do with integrals, and so even more general thing is almost equally easy to prove this equation 7, but this equation 7 has a name. It is called Markov inequality, and may have been part of a PhD thesis of Markov in the towards the end of the 19th century. 19th or 20th, I forget how the centuries are counted. So somewhere around 1880s, 1890s, the proof was there by Markov, and it's something tool which is used a lot. Okay. And I want to again repeat that all that we discussed and most of what will follow can be seen as a discussion on sequences and series of real numbers. Okay. Okay. Now we come to another interesting. So expected value of x squared is finite. So x is a function, real valued. So x squared is also a function, real valued, and it is positive. The square of the function, so it's positive. So expectation is always defined. So suppose expectation x square is finite. Now use the simple mod of x is always less than or equal to 1 plus x square. We can even more, we can say 2 times something, but let's forget that. This is a trivial thing. X is less than or equal to 1 when it is this one, and if x is bigger than 1, then it is the second one. So it is always less than or equal to 1 plus x square. It follows that, expectation x is defined because expectation x square is finite, and monotonicity and so on and so forth, one can verify that expectation mod x is finite. So expectation x is finite, therefore expectation x is defined, it is mu, let's say. Now you look at expected value of x minus mu square. Since x minus x, this expectation is expectation x square minus 2 mu x plus mu square. Mu is a constant, so in the summation or expectation mu will come out, so the expectation here will be minus 2 times expected x, and the last one is mu square. So this one will give you minus 2 mu square, here we'll get plus mu square, so total will get minus mu square. So we come up with variance x equal to expected x square minus mu square. And this is what is called variance in statistics. And now we have this inequality, probability x minus mu greater than or equal to epsilon, which is same as this, and applying Markov inequality will get this. This inequality is called, I don't know how to pronounce the French name because it's not much used in literature. It's just known as Chebyshev's inequality, but careful reading of this says that these two they were friends, they were communicating with each other, and the best way to describe now it is agreed is that you have to call it Binet-Chebyshev inequality. And of course, the proof given here is not given by them. These were in 1850s to 60s. At that time, probability was viewed differently, and they wrote in like pages after pages explaining this. If this were not true, then the contribution to the variance coming from such points will be more blah blah blah. And Markov, who appeared in the previous slide, was actually a PhD student of Chebyshev in Russia, and he came up with these tools to give a more understandable and more convincing proof of Chebyshev inequality, amongst other things. That is not the only thing Markov did, but of course they were not confining themselves only to countable set of omega. Then it is trivial to prove, as we have seen. and not that they couldn't do it, but they wanted more generalities, and that's where the difficulties came. But they remain very powerful tools even today. Okay, and the variance term is written as var x, or as a term, as a standard notation in statistics books, primarily also in probability books. For the expected value is mu, and for the variance is sigma square. But okay, so this is a I'm coming to the Weierstrass approximation theorem. Let's recall Weierstrass approximation theorem is that you have a continuous function on a unit interval, then it can be approximated uniformly by polynomials. That is the Weierstrass theorem or Weierstrass approximation theorem. We either here read it as Weierstrass, study it as Weierstrass theorem, or we see directly Stone-Weierstrass theorem, where it is a more abstract version of this is stated, and then the proof is all mixed up with the existential proof. But for reals, there is a constructive proof, and here is the constructive proof. So let's do the following. Take n to be bigger than it. N is a fixed number, and fix a t, and n and x be a random variable with this distribution. So this is a terminology used a lot in probability, and what we mean here is, let us take our set omega that we talked about as 0, 1, 2 up to n. Our random variable can take values anything between 0 to n. So our omega is a n plus 1 numbers, 0, 1, 2 up to n. And binomial theorem will tell us that the right hand side quantities are such that summation over k equal to 0 to n is going to give us t plus 1 minus t to the power n, which is going to be 1. So if we have deliberately not written it here, this is what we mean by distribution of a random variable. So you list what values it takes and what are the associated probabilities. As long as they add up to 1, we need not worry how this omega was constructed. Okay. So we can move away from defining omegas and writing little omegas and all that to just describing random variables. Okay. Then if need be, if challenged, we can write down what omega will be. All right. That's the view to take. So let x be a random variable with this distribution. Then using simple algebra, of course, we can very easily see that expected x will be nt. So you have to take n times summation, and variance you have to take n square times summation. Very little tricks will be needed to verify that the mean or expected x is nt and variance x is n of n times t into 1 minus t. It will appear on the next screen, but without using the term probability, expected value and variance, this computations, that summation of this n times this is nt and summation of n square and minus something something is equal to nt 1 minus t appear in Simmons' book. Okay. So, all right, Simmons' book on Introduction to Analysis Topology. The exact thing will come on the next scene. Okay. So now let's do the following. Given a continuous function f, let us define weighted average of f of k by n. So k is between 0 to n. So k by n will be between 0 to n. So f of k by n will be some value on our interval. And the weights are taken by this. Weights are dependent on t. So our gn of t is defined as follows. Okay. Now, by using the Chebyshev inequality, one can verify that supremum over t, gnt minus ft converges to 0. Of course, because everything is only finitely many, we don't have to do all that. One can just do a very simple analysis and write down that it converges to 0. That is what Simmons does in this book, Introduction to Geometry, Topology and Modern Analysis. I've given the pages. He even gives the name that this polynomial introduced, G and T, is called Bernstein polynomial. The book I have checked several times. There is no reference to where this polynomial occurs in Bernstein's work. If it is called after Bernstein, presumably Bernstein defined it. There is absolutely no reference. And there is no reference to probability or Chebyshev inequality or expectation of variance. Nothing. Just the proof is written out as ab initio. Interestingly, Bernstein, we can speculate why did Bernstein come up with this construction, and it becomes abundantly clear when one tries to locate the source where it appeared. And though we may not need to understand what the French to understand that he had essentially probability in mind, because the proof of Weierstrass something using calculus of probability. That is the title of his paper, 1912-13. And today, sitting at home, I can locate where and get exactly a screenshot of that paper.